Have you ever wondered why summer nights remain remarkably bright in certain cities? This stunning phenomenon is called white nights, when evening twilight seamlessly blends with morning twilight. Atmospheric air scatters solar light even when the luminary has completely dropped below the horizon line. Rigorous mathematical formulas easily calculate the exact duration of this beautiful astronomical phenomenon.
The line separating day from night, it's not a sharp edge, is it? It's more of a gradient, a beautiful, gradual zone of scattered light that we call twilight. So, to really understand this phenomenon, and especially its most extreme version, the white nights you see in high latitudes, we have to examine the precise interplay of astronomy, geography, and of course, mathematics. So, let's begin. To start, we really have to tackle the fundamental mechanism here. How is it even possible that we can see light when the sun is no longer visible in the sky? Well, you can think of twilight as essentially borrowed light. See, even after the sun is physically dipped below your horizon, its rays are still traveling through space, and they strike the upper layers of our atmosphere. The molecules of air way up there act like countless tiny mirrors, scattering that sunlight in all directions. Some of that scattered light gets redirected back down to the surface, and that's what creates the diffuse glow we experience as twilight, both in the evening after sunset and in the morning before sunrise. Now, to analyze this period with any scientific rigor, we have to classify twilight into distinct stages. Each one is defined by the precise geometric position of the sun below the horizon. And these aren't just arbitrary labels. They actually correspond to real-world, observable changes in the light around you. The distinction we draw between civil and astronomical twilight isn't just academic. It's based on very practical, observable thresholds, which we're about to explore right now. First up, we have civil twilight. This phase lasts from the moment of sunset until the center of the sun's disk hits 6 degrees below the geometric horizon. The name civil is a pretty big clue, right? This is the period where civic life can still go on. There's enough ambient light for most outdoor activities without needing streetlights, and you'll start to see the brightest stars and planets pop out against that fading sky. Then we have astronomical twilight, which ends when the sun reaches a full 18 degrees below the horizon. At this point, that last bit of residual sunlight scattering through the upper atmosphere has finally faded away. The sky is now dark enough for astronomers to observe the faintest celestial objects, like distant nebulae and galaxies. For them, this marks the beginning of true night. You know, there's a common misconception that twilight lasts for the same amount of time everywhere on Earth, but in reality, its duration is incredibly variable. It all depends on where you are and the time of year. But the great thing is, this isn't a mystery. It's a variable we can calculate with some very satisfying mathematical precision. The duration of twilight is really just a function of how long it takes the sun to travel from the horizon down to a specific negative altitude. And we can calculate that using this formula. Now, I know it looks a little intimidating, but it simply relates the sun's position to 3 key variables: your location on Earth, the time of year, and which twilight boundary we're actually measuring. So let's break each of these variables down. The first variable, and probably the most intuitive one, is your geographic latitude. That's denoted by the Greek letter phi. It's simply your position on the globe, north or south of the equator. Now, the crucial part is that your latitude determines the apparent path the sun takes across the sky. If you're near the equator, that path is very steep, but near the poles, it becomes much, much more shallow. The second variable is the solar declination, or delta sun, and this is a direct result of Earth's 23.5-degree axial tilt. As we orbit the sun throughout the year, that declination changes. That's what gives us our seasons, and it also alters the sun's path in the sky for any given day of the year. And finally, we have the sun's altitude, h-sun. This is the part of the formula that defines the specific boundary of the twilight we're trying to measure. So just like we discussed, we'd plug in -6 degrees to find the end of civil twilight and -18 degrees to find the end of astronomical twilight. Okay, now that we have those variables, this is where things get really fascinating. Because at very high latitudes, these 3 variables can conspire to produce a truly remarkable effect: a night without any true darkness at all. So how do these white nights actually happen? Well, it's a sort of perfect storm. You're at a very high latitude, so the sun's path across your sky is already extremely shallow. At the same time, it's near the summer solstice, so the solar declination is at its highest value. You put those 2 things together, and the sun, even as it travels along that shallow path, simply never gets low enough below the horizon to end twilight. It just kind of lingers there, causing the evening twilight to merge seamlessly into the morning twilight. A classic textbook example of this is St. Petersburg, Russia. It sits at a latitude of approximately 60 degrees north. So right around the summer solstice, when that solar declination is at its peak, the sun's altitude at solar midnight, its lowest point in the sky, is precisely -6 degrees. This means the sky never, ever gets darker than civil twilight, which results in the city's famous and absolutely beautiful white nights. And this isn't just limited to one city or even one type of twilight. As these conditions here show, there are specific mathematical relationships between your latitude and the solar declination that determine when you'll get civil or even astronomical white nights. The big takeaway is that for any latitude beyond 48.5 degrees, either north or south, there will be some period of the year where the sky never gets truly dark enough for deep space astronomy. All right, there is one final crucial physical principle we have to consider, and it's all about the way our own atmosphere bends light. You see, because our atmosphere has a density gradient, it gets thinner the higher up you go, it acts like a giant lens. So as light rays from the sun pass through it, they get bent. This phenomenon is called atmospheric refraction, and it means that the perceived position of the sun isn't its true geometric position. In fact, we actually see the sun appear on the horizon when, geometrically, it is still entirely below it. So just how much of a difference does this make? Well, you have to add two effects together. The refraction itself accounts for about 35 arc minutes of bending. Then you have to add the sun's own radius, which is about 16 arc minutes. So put it together, and it means that when we perceive the very top edge of the sun touching the horizon, its geometric center is actually 51 arc minutes below it. That's just shy of a full degree. That's how much extra daylight we get just from atmospheric effects. And this systematically lengthens the perceived day for everyone, all across the globe. It's the reason why, even at the equator, day is always slightly longer than night. And it's also why the true equinox, a day of exactly equal light and darkness, doesn't fall precisely on the astronomical date you might think it would. So as we've seen, our experience of light isn't a simple on-off switch. It's a whole spectrum, and it's governed by these precise astronomical definitions, and then altered by the physics of our own atmosphere. From the functional brightness of civil twilight to the profound darkness required for deep space astronomy, each stage is both measurable and predictable. So in the end, that simple transition from day to night is revealed to be this complex interplay of geometry and physics, a gradient that's defined by calculation, not some sharp, simple line. And that brings me to a final, more philosophical question. If the boundary between day and night, something that seems so absolute, is in fact a measurable continuum, what other clear divisions that we perceive in our world might also be revealed as fascinating, complex gradients if we just took a closer look?
Thank you, friends. Strive for understanding and become wiser. See you soon.